Our theme song today, it's pretty easy to make the connection.
What was the theme song?
What's in 1 week? It's the exam. I got a bagel watch. Alright, so dropping off Sadie was fine because we took her to place the Green Spring Pepper Store, which I highly recommend. And probably shouldn't advertise for them in class. And so they were like, all right, Sadie, let's go back. And so I prepared myself, and then Sadie just walked right back up, didn't even look back at me. It made it a lot easier, actually. I was like, all right, Sadie, well, same to you. All right. And I picked her up this morning. Okay. Sorry for the weather. It's a perfect day for a super oversized flannel shirt. I brought the cold back with me, I guess. We went to that wedding. My wife was in a dress, and our hotel was about a mile from the wedding, and so we decided to walk it because weddings and drinking, and you don't want to mess around with that. Well, we didn't end up drinking that much, but it was like 23 degrees on the walk back, and so it was really cold. Michigan, I don't miss that. Okay, so the exam is I really didn't get bagel watch. The exam is in a week. We had our homework due on Friday. We've got another homework this upcoming Friday. We'll have an office hour at least once every day this week. Wednesday, technically, I'll roll that into the workshop from 4 to 6. But yeah, so today's office hour today is 2:30 to 3:30. So those have been really, really good. I think people are having a lot of clarifications whenever they get to those. So I highly recommend it. All right, so we'll continue our journey through different reactions today, and I think my numbering is way off on this because I've been skipping a few things. So I think we did reaction number 4 on our table. Is that right?
No.
3. Okay. So we'll move forward now to you, and we'll do what is to you reaction number 4. All right, and so we can give this one a nickname. Not all of these have nice and neat names, but we can give this one the name of the halohydrin reaction. All right, so the first part is halo, and so what do you think that means? Halogen, and then the second part is hydrin, which sounds a little bit like hydrate, which sounds a little bit like water, right? And so basically that's what it is. We're going to end up adding a halogen and then a water molecule. At least we'll end up with a similar product as if we had added a water molecule. So to take a look at this reaction, we'll start with a trusty starting material of this thing. And so what we're going to do is we're going to introduce a molecule that looks like this. And so we'll have chlorine. So that's going to be connected to an OH group like that. All right, so based on the fact that we've been going through the halonium type mechanisms, what do you think the first step of this is going to be? Not protonate, because that would lead us to a carbocation, and we don't go through a carbocation with halonium type mechanisms. But so what do? Yeah, so we form that 3-membered ring, right? So if we were treating this with Cl2 instead of ClOH, we know we would form a 3-membered ring. That's our halonium, in that case, a chloronium. And so that's exactly what we do. Now, of course, we are going to start our arrows where? Electrons. And so we'll start our arrows there. So we're going to draw to the chlorine. And so why are we going to draw to the chlorine?
More electronegative?
Well, if it were more electronegative, that wouldn't make a lot of sense because we're connecting it to electrons that are already negative, right? And so between oxygen and chlorine, if you look up on the table, you find that they have very similar electronegativities, but oxygen is more electronegative. And so what we end up with is a partial negative on that side and a partial positive on that side. And so electrons being negatively charged, they're going to be more attracted to the partial positively charged side, and so that's what happens. So this does leave, so just like we've seen before, we kick that thing off. And so at the same time, we don't want to form a carbocation because we are able to stabilize the potential carbocation by essentially taking one of the lone pairs on the chlorine and re-adding it back in. So in doing so, we're going to end up with the chloronium intermediate that we've seen thus far. Okay, so when we add or when we form a halonium, what is a specific, geometrically speaking, what do we have to do considering the sides of the double bond? Does it add to the same side or can it add to opposite sides? Always is going to add to the same side, right? And that's just a geometric thing. It has to reach out and grab an orbital, and so clearly the orbital that is closer to it is going to be a lot more easily grabbed. And so we end up with an intermediate that in this case will look like this. All right, so we've added our chlorine to the same side, and so we have a positive charge on the chlorine now. All right, is that the only product or the only intermediate that would form?
No.
All right, so what would we say? What else could happen? It could come in from the back, right? And so we could, instead of drawing out that picture, what could we say? We could just say, yeah, we have this plus we have the enantiomer. Both of those products are going to be possible. All right, so then of course, what we've got floating around is some OH minus. Now, if we've seen water can be relatively nucleophilic, do you think OH minus are going to be more or less so? It's going to be more so. Now we're concentrating electron density even more on that oxygen, right? And so it's going to become even less stable, and it really wants to go out and grab some area of positive charge. So we absolutely are now going to treat our hydroxide as a nucleophile. And so we've got two possibilities, right? We already talked about why we wouldn't add it to the chlorine, so that wouldn't lead us to a productive product. So we're going to add it to one of the carbons, either this top carbon or this bottom carbon. And what did we decide? It wasn't the bottom carbon. And so what we thought about is we thought about the fact that this chloronium intermediate is going to be in equilibrium with a couple of other intermediates. And so we saw that one of those intermediates had a positive charge on the top carbon, and the other intermediate had a positive charge on the bottom carbon. And so where would a positive charge be more stable, top or bottom? Top, right? Because it's a tertiary carbon, for the same reason that we know a tertiary carbocation is more stable than a secondary carbocation. So, when we consider these two carbons, we would consider this one to be a little more positively charged, and the bottom one to be a little more negatively charged. And again, it's just because the top one is a tertiary and the bottom one is a secondary. You can almost just kind of consider those two carbons as carbocations, which would be more stable, and that's going to be the one that's attacked. All right, so our hydroxide will attack that carbon. So we learned that it has to attack from the backside, right? And so if it attacks from the backside, that chloride is on a wedge, and so it's going to push that chloride off, but to approach it from the backside, from 180 degrees from that wedge, where's it going to end up? On a wedge or a dash itself? Yeah, on a dash. And so what we end up with is we have our hydroxide has come in. It's going to be on a dash because it's approached from the backside of the chlorine. Yeah.
So if the methyl group were on a wedge, would the hydroxide be on a wedge afterward?
Well, if the methyl group were on a wedge, then we would have to have our chloride on a dash, right?
Yeah.
And so in that case, yeah, we would approach from the opposite side. And so I can draw out both of those products just so that we know exactly what we're talking about. So the enantiomer, if our methyl is on a wedge, we would end up with our chloride on a dash like this. So when we add our hydroxide in, we know that we have to approach from the backside of our chlorine, right, which is being displaced. And so if our chlorine is on a dash, what is the backside of that? Front or back? It's going to be front, right? And so we end up in that case with a hydroxide on a wedge, right, if it comes in from the front. So in that case, we would now have our hydroxide on a wedge, which would push our methyl to be on a dash. And in the top case, we pushed our methyl forward to be on a wedge. And so in the top structure, all right, we're lacking just one more thing now, right? The chlorine. And so is the chlorine on the bottom going to be on a, or I'm sorry, in this top structure, on this carbon, will it be on a wedge or a dash? It'll be on a wedge, right? Because we haven't really done any chemistry there. We've just, that bond stays still. And so the alternative is true on the bottom. We have our chlorine on a dash down there. All right, so if you were asked about the stereochemistry of this reaction, would you say that it is syn or anti? It is anti, right? And it's anti because our electrophile the chlorine, and then our nucleophile, the OH, they end up on opposite sides, right? So it's going to be an anti-addition. All right, so we can add this to our table. This is reaction number 4. Yeah.
Why? Could you explain like how it has 2 going to the chlorine and then why it drops to just 1? 2 wedges going to the.
Yeah, and so what it is we're essentially, the chlorine doesn't want to make 2 bonds, right? Because the chlorine making 2 bonds has a positive charge. It ultimately wants to make 1 bond. And so what we've got is, because we've got a nucleophile in here like the hydroxide, what we can do is if we form a new bond in at this position right here between the oxygen and the carbon, what that's going to do is well, for one thing, that would make 5 bonds to that carbon, right? And so 5 bonds isn't allowed. So what we've got to do is we've got to break a bond. And so the bond that is basically wanting to break already is going to be this carbon-chlorine bond, because the chlorine's bonded to 2 things and is relatively unhappy. And so that's exactly what will be happening. In fact, what we can do, and what we should do, is go ahead and draw an arrow like that, showing that that bond, the electrons in that bond are going to be going back to the chlorine. All right, so we can do that. And so basically, if we didn't break a bond, we'd end up with 5 bonds on carbon. So we've got a bond that is happy to break, and so that's the one that does break.
And it has to go opposite the chlorine.
Yeah, it has to be from the backside. It has to approach 180 degrees from the chlorine itself. And so if the chlorine is on a wedge, it's going to have to approach from the back. And then vice versa, if the chlorine is on a dash, it will have to approach from the front. Yeah.
So if we didn't have a methyl substituent, then it would just be like as likely to just form from go on the top or the bottom, because you wouldn't have a tertiary versus secondary.
Yeah, and so in that case, you could end up adding to either the top carbon or the bottom carbon, because they're equivalent basically in how stable the carbocation would be. And in that case, I think what you would find is you'd still only form 2 products, because of the symmetry in the molecule, you would end up with the same thing. Yeah. All right, so this is reaction number 4. And so the electrophile that we are adding is what? Yeah, so we end up with a chlorine, so that will be what we call our electrophile. And in fact, let's not call it a chlorine, let's call it an X, because there are a couple of possibilities. So we'll specify that as just an X.
Is it always a halogen?
Yes. All right, and so our nucleophile is what? Yeah, so it's going to be an OH like that. That's what we end up with as our nucleophile. All right, so the reagents that we'll see used in these reactions, so we've already seen ClOH. You'll also see BrOH, and so those are the 2 things. Just like the previous reaction number 3 where we said it could be chlorine or bromine, it's the same case here. We have chlorine and bromine that are going to form these halonium intermediates. You'll also see a couple of other possibilities. So you could see the reagent Cl2 and H2O, or you could see Br2 and H2O, and I'll walk you through that mechanism in just a second. Very similar. All right, so the regioselectivity, would you describe this as Markovnikov or anti-Markovnikov? Markovnikov, right? Because we're adding our electrophile to the carbon with the most hydrogens, and so it is Markovnikov. What about the stereoselectivity? Anti. So we can call it an X plus, or the 3-membered ring, X plus. All right, let's see how that other group of reagents works if we want to do this reaction. So in that case, we'll start with the same starting material. And so let's use Br2 and H2O. So H2O by itself is not going to be reactive, and so what we're going to do is very similar to reaction number 3 when we added our halogen, is we're going to start this thing the same way. So we take our double bond, our alkene, and we add it to the bromine. And so at the same time, the other bromine leaves, and then one of the lone pairs from the first bromine, the electrophilic bromine, adds back in. And so what we end up with in this case is the polonium that we've been drawing all along. In this case, a bromonium. So that's going to be on the same side, and of course we could have the other addition, so it's going to be this plus is enantiomer. And so what have we got left in solution? We've got Br minus, and we've got H2O. And so we've already seen a case like this, right? Or a lot like this. Between these two things, which is going to be more nucleophilic? Definitely H2O again. And in this case, probably what you would do is you'd run the reaction with lots of H2O and just enough bromine to get the reaction going. But yeah, again, we've already said that H2O is more nucleophilic. And so because H2O is more nucleophilic, when we displace our bromine, it's going to be done by the water, not by the additional bromine. So our water, if it's approached from the backside of our wedged bromine, will be on what? It'll be on a dash. And of course, it's not just an OH because we added the entire water itself, and so we want to show that. So we've essentially moved our positive charge from the bromine to the oxygen. Our methyl is now on a wedge. And so how do we ultimately end up getting to a neutral product like we always want to do? Yeah, we're going to deprotonate that OH2 group, and so you can use just a generic base if you'd like to do that. And so what we end up with, and this is still plus enantiomer, what you end up with is essentially the same product as above. This plus enantiomer. So there's two different ways that we can ultimately do this halohydrin reaction, either with BROH or with Br2 and water. We end up ultimately getting the same product in both cases.
Oh, we do that second bromine. It just kind of.
Yeah, and so our second bromine, it's going to end up right here. It's just a counter ion to that positive charge. Then, of course, really what we would end up with is something that looks like this. And so our bromine, again, is just going to be a counter ion. It's a spectator. Bromine as a base is pretty non-reactive, and so it's just going to be there to counter the positive charge that we're always going to have somewhere at some point in the mechanism. All right. All right, again, I'm going to skip ahead a little bit. All right, so we'll do one more halonium type mechanism. This is number 5. All right, so our reaction number 5, we're going to refer to as oxymercuration oxidation. Okay. So this is a pretty good one. So we'll just draw the overall scheme of what's going on first. So this is going to be a two-step reaction. Essentially, sometimes what you're going to find is sometimes you end up with not intermediates that are very high in energy. Sometimes you end up with intermediates that are pretty stable, but it's still not the product that you want. So we end up doing what we'll call a workup. And so once I show you the example of that, we'll see that workups are typically oxidative reductive, but it's simply just going to convert our stable intermediate to whatever the product is that we want. And typically, we don't worry about the mechanism either. We just say, well, it just goes from this to this with our workup. All right, so, and then oxymercuration oxidation, we're going to start with mercury acetate. So once we react with mercury acetate, we're going to end up with some stable intermediate, but again, it's not the product we want, and so we hit that with a compound called sodium borohydride. And so what this is our workup step, and so it essentially converts a stable intermediate our desired product. All right, so the ultimate product that we end up getting, you've seen before. It would be this product. Okay, so we've already learned a different way to make that product. What was it? It wasn't halohydrin, because in a halohydrin reaction, we end up with our electrophilic halogen on this carbon right here, right? So what about if we reacted with H2O and then a little bit of catalytic acid? Right, and so what we end up with in that case is we would protonate at this position, and so we have a tertiary carbocation that our water would attack, and so we ended up with a very similar product. But what we're going to see in a minute is that there's some benefits to doing it this way. What do you think, just intuitively, based off what we've learned about carbocation mechanisms versus halonium mechanisms, what do you think could be a benefit? Yeah, what do I keep saying about carbocations? They're messy. There's lots of possibilities, right? Lots of different stereo possibilities. And so with this sort of mechanism we've seen, in this halonium mechanism, we see that it's more stereo controlled. And so let's look at what this mechanism is. So to do this reaction, we're going to have our mercury acetate. All right, so it looks like that. So what we've done is we've got our partial positive and our partial negative there. And so how do you think the reaction's going to start? Remember, this is still just a type 2 mechanism, and so the beginning, definitely the beginning of the mechanism is going to be exactly the same. So where do we start our arrow? Which electrons? Up the pi bond. And so it's the same thing we'll do here. So we start our electrons at the pi bond. So I didn't draw these in, but what we've got is a lone pair, or really, what we can do. Yeah, we'll just show a lone pair there. Okay, so based off of everything we've done, we kick off that part. And so we've done that at every point of the mechanism, right? We've kicked something off once we've done our first addition. And so at the same time, what we're going to do is take this lone pair and add them back in to our potential carbocation. And so in doing so, what we're going to form is going to be something that looks like this. So it's going to be a halonium type intermediate, but instead of a halogen, essentially what we're going to have is mercury in its place. So even though it's not a halogen, we're still going through that type of mechanism. And so we've got water in our reaction, and so how do you think water is going to interact with this intermediate? Could water be a nucleophile?
Yeah.
Absolutely. And so do we have a three-membered ring that we probably want to break open?
Yeah.
Yeah. And so where's that water going to add? To the top carbon or the bottom carbon? Top carbon, right? Following the same exact rules we've learned all along. Yeah.
Why is the OH still attached to the hydrogen?
Well, because there's two, right? And so we lost one of them, but the other one's still there.
Okay,
Yeah.
where did the other one? Where did the other one?
It's a counter ion. And so we've got a positive charge, and so we've got to have a negative charge somewhere. So it's just there. Yeah. Okay, so using everything we've learned thus far, and of course this is also plus an enantiomer. We'll start our next step. The same way that we've been doing it all along. So what we end up with, all right, so let's see, we've got our mercury acetate on a wedge. And so our water, it had to approach from what? How did it approach that? From the backside, right? And so if it's approaching from the backside, is it going to end up on a wedge or a dash?
Dash.
On a dash. So it's still going to look like this, which means our methyl is now on a wedge. And so we're not doing neutral products, so what do we need to do? We need to deprotonate. And so in this case, you can use a generic B. You could use this thing right here, this acetate ion, to deprotonate. And so what we end up with is going to be an OH on a dash, a methyl group on a wedge, and mercury connected to our product. All right, so have we seen basically this exact mechanism already? Yeah, absolutely. It's the same mechanism, and that's why I keep driving home the point. Is these mechanisms, they're all going basically through the same steps. We're just kind of substituting in different atoms. Mechanistically, they all work the same, and so this goes through a halonium-type three-membered ring. But we don't want to end up with mercury on here. Mercury is not, I guess what we would say, ideal to have on our organic structure. Not a lot. Any of the drugs that I've shown you, they haven't had just a mercury sticking off of them. And so what we're going to do at this point is we're going to hit it with our second step. So this would be our workup. And so we've got our sodium borohydride. And so sodium borohydride is basically is the equivalent of a hydride like that. And so essentially what happens is it's going to swap out with the mercury, and that's it. We don't care about mechanistically what's going on. We just want to say, well, that mercury gets converted to the hydride and we're done. It's a workup step. It's a way that we get rid of the mercury and we get the hydrogen in its place. And so what we end up with, so here we've got plus an enantiomer still. What we end up with is essentially going to be this product right here. So we more or less have swapped out our mercury and put in a hydride. Don't worry about mechanistically what happens. I'm not totally even sure how that works. Okay, so the question we would ask ourselves, because we've already talked about the fact that, well, we can do this Markovnikov addition of water using water and sulfuric acid, and so why on earth would we ever consider using mercury? Because, well, toxicity-wise, what's mercury like? It's not ideal, and so it's the same thing in the lab. You know that mercury is toxic, and you don't want to work with mercury if you can help it, but it does have some benefits, and so we can ask ourselves the question, why use our mercury acetate sodium borohydride reaction in place of H2O catalytic acid. And so we've got two good reasons. So number one, since we're going through the halonium type intermediate, we're getting anti-stereoselectivity. And so we say number one, the anti-stereoselectivity gives fewer products, which is always a good thing. And then furthermore, by going through by avoiding a carbocation, what are we also avoiding? What can happen with a carbocation, but not a halonium? 1,2 hydride shifts or 1,2 alkyl shifts. And so by doing this chemistry as well, we avoid going through that carbocation, dealing with any carbocation rearrangements that can take place. So avoiding the carbocation allows us to avoid 1,2 shifts. All right, so those are two very good reasons that are going to simplify the products that are going to come out the other side of this reaction. All right, so let's add this guy to our repertoire. So this is number 5. And so the electrophile that we end up with on our product is what? What do we end up with on the secondary carbon at the end? It's just a hydrogen, right? So because of our workup step, that simplifies that to be just a hydrogen. And so what's our nucleophile? OH. And so we've seen that this is going to be a 2-step reaction where we have mercury acetate and water. And then our second step is going to be sodium borohydride as a reducing agent. That's our workup step. The regiochemistry. Yeah, it's Markovnikov, right? Because we end up with our electrophile on the secondary carbon, so it would be Markovnikov. What about the stereochemistry? It's anti because we're going through a halonium type mechanism, and so I'll just add that over here. And so I think that's going to be it for halonium type mechanisms. So basically we saw that halogens can do it, but now we've also seen that mercury can do it in a way where we've already formed this Markovnikov addition of water to our alkene, but now we can do it in a more stereo-controlled way without the possibility of carbocations forming. So this would be a more likely way that you would actually do this reaction. All right, so I think that puts us on Roman numeral 7. And so that leads us to our final type of mechanism. So that's going to be mechanism type 3. And so what we'll do is we'll call this one concerted. All right, so we'll, to abbreviate, we might use concerted like that. All right, what does concerted mean when we're talking about a reaction?
What does concerted mean? Never heard of what concerted.
It means that the electrophile and the nucleophile add at the same time.
Okay.
And so instead of going through these intermediates, such as the carbocation, which then gets added into by the nucleophile, or the halonium, where one of the carbons gets added into by the nucleophile, now we're just going to add them at the same time. So really, it seems like a more simple mechanism, and so it really kind of is. So let's talk about a general look at this sort of thing. All right, so we've got an alkene like this, and so let's think about this pi bond for a second. So can we draw resonance structures using this double bond that I've drawn?
Oh, yes.
Yeah.
I think we can. So if we drew this, we would end up with a lone pair here, negative charge, positive charge there. All right, is that a valid structure based on our rules?
Yeah.
Yeah, we've said it's okay to have open shell carbon, so that's perfectly fine. And so what we're really kind of learning about is I guess, the true nature of alkenes here. And so there is possible resonance. And so what that means is we're going to end up with a couple of different intermediates. Now, what we want to focus in on is that positive charge. Okay, so let's actually just rank these using the rules we've learned. What's the most stable?
Middle.
Undoubtedly the middle one. Why? Closed shell, right? So this is the most stable one. So now let's consider those other two resonance structures. All right, so which is going to be more stable?
Right one.
Let's just consider the positive charge, not worry too much about the negative charge. What's a more stable positive charge?
Left one. Definitely the left one. It's a tertiary carbon.
Yeah, so the positive charge in the blue case is on a tertiary carbon. We're essentially looking at a tertiary carbocation versus a secondary carbocation. And so which is more stable? Tertiary. And so is it going to be blue or red that's more stable? It's going to be blue. So that's our second, and that's our third. And so if we think about our initial alkene as each carbon having a partial positive or a partial negative, because this blue structure is going to make more of a contribution than this red structure, what we would say is that the top carbon has a little bit of a partial positive charge, and the bottom carbon has a little bit of a partial negative charge. And again, that's just based off of the resonance structures, right? The true nature. Now, this double bond certainly exists as this thing 99.9% of the time, but there is a little bit of this characteristic as well as a little bit of this characteristic, and that lends a little bit of a charge to each of those carbons, and ultimately is going to change the reactivity just a little bit that we see a certain pattern emerge. Okay, so if we draw it out this way, we want to use a generic nucleophile electrophile combination. And so between that nucleophile and the electrophile, which one has a partial positive charge? The electrophile, and so that means the nucleophile has a partial negative charge. Do you see something, have these things kind of lined up in a natural order? Yeah, so we've got our partial positive charge on top, and and our partial negative charge on top as well. And then vice versa, we have two opposite charges on the bottom. And so the reactivity that we see basically is going to follow that order such that we're going to start our double bond, we're going to draw it to our electrophile, and then at the same time, this sigma bond right here between the nucleophile and the electrophile is going to snap to that partially positively charged carbon. Okay, so what we end up with in this case is very specifically, do you think that this is going to happen on the same side or on opposite sides?
Opposite sides. Same.
Let's think about what this would look like maybe if we turned it on edge. So if we did that, we would have carbon. All right, so let's say that this is a tertiary and the other side is a primary. And so in that case, we would end up with our electrophile here, because our primary would have a partial negative. Well, this has a partial positive, so we have a partial positive this side, partial negative this side. So ultimately, when we draw our mechanism, is it going to be really possible for the nucleophile to approach this from the bottom face? No, it's pretty much going to have to come from the top face, right? And it's because it's already there. If it's happening at the same time, it's still stuck to this electrophile, which is reacting here on the top side. And so what's going to happen is, in fact, the nucleophile will go in that direction. So what we end up with, do you think it's going to be syn or anti? Syn. Definitely going to be syn. So our nucleophile is added in there. Our electrophile is added in there. So we've done this all in one step. And because we've done it in one step, geometrically, the only way these things can snap together is going to be on the same side. And so that's going to be one of the characteristics of these concerted mechanisms, is that it's going to be a syn addition, unlike the anti-addition that we've seen in our halonium mechanism. All right, of course, we also have here plus an enantiomer, because the nucleophile could have come in from the opposite face, right? So we could have added in from the bottom. So, when we talk about the regioselectivity of these concerted mechanisms, what we want to specify is that we want to match our partial negatives to our partial positive. That's what we really want to focus in on. We want to make sure that we're lining up our reagent in the same, or at least the opposite polarity direction as our double bond. And then for the stereoselectivity, syn or anti? Syn. And so we're always going to have the syn addition product. Okay, so that's our concerted mechanism, and so we'll jump right into some reactions. And then, my goal is, I'm thinking we might be able to pretty much be through the reactions on Wednesday, and then on Friday we can just talk about some nuances and try to get prepped for the exam on Monday. So we'll see what kind of time we have. All right, so let's consider something. Actually, let's first, what Roman numeral are we on now? All right, so we're now on Roman numeral number 8. And this would be concerted reactions, okay? And so let's consider something we can already do. So for example, if we had this product right here, going in the right direction, we could, let's see, there's two things we could do. We could add H2O and catalytic acid, or we could do our oxymercuration, so mercury acetate, and then sodium, or a hydride. And so what we're going to end up with the same product in both cases, and so we're going to ultimately end up with an OH on one of those carbons. And so is it going to be the primary or the tertiary? It's going to be the tertiary, right? Because we've seen that both of these reactions have Markovnikov regioselectivity. And so the product that we end up with in both cases would be the product right there. But let's say we're synthesizing some drug And we need to turn this into an alcohol, but we don't need to turn it into that alcohol. Let's say we actually needed to turn it into the alcohol where the hydroxyl group is actually going to go on our primary carbon. And so up to this point in our toolbox of reactions, we don't have a way to do that. But you probably see where this is leading. We're about to learn where we can essentially reverse the regioselectivity and so make the other alcohol. And so in that case, what we're going to do is we're going to hit it with BH3, followed by a workup step of hydrogen peroxide and sodium hydroxide. And so what we end up with, in this case, is going to be that primary alcohol. So this is a really important synthetic element. Really, this is the first time that we've had an opportunity to use our reactions that we've learned to maybe diverge and make similar products, but now having different regioselectivity. So this is pretty cool. And this is the sort of thinking that goes into being a synthetic chemist. If you're a synthetic chemist, you know that you need to convert one group to another group, and eventually, you can end up with syntheses that are going 20 or 25 steps even, right? You have simple molecules to start with, and then you just build complexity as you go. But sometimes you have regioselectivity issues, and you can have stereoselectivity issues. And what you need to do as you go along is you need to be thinking about, well, which reagents are going to lead me to the correct product, right, with the right regioselectivity as well as the right stereoselectivity. So we've got two options now for adding our alcohol. Which reaction number is this? 6? Yeah, all right. So number 6 we're going to call hydroboration, followed by oxidation. Hold on. All right, let's go back really quickly in your notes. I called it an oxymercuration. Oxidation. It's actually going to be an oxymercuration reduction. My apologies. All right, so just instead of calling reaction number 5 an oxymercuration oxidation, it's oxymercuration reduction. I misspoke, or miswrote, or did both. All right, so in a hydroboration oxidation, let's see how this mechanism works. It's going to be a concerted mechanism. And so our BH3 will align like this. All right, so we've already seen why we're going to have a partial positive there and a partial negative there. So let's think about that boron-hydrogen bond. What's more electronegative? Is it going to be boron or hydrogen?
Hydrogen.
Yeah, so it's actually going to be hydrogen by a little bit. I believe it has a number of 2.1 on the Pauling scale, whereas boron has a number of 2.0. And so hydrogen's its own little beast over there on the periodic table. It doesn't really follow the trend as well. So what we end up with is a slight partial negative there, and a slight partial positive there. And again, it's because of the 2.1 versus a 2.0 on the Pauling scale. They're slightly different. Kind of bucks the trend. Hydrogen is its own thing. All right, so when we draw our mechanism, have we got it aligned correctly?
Yes.
Yeah, right? We've got our partial negative down here matched to our partial positive, and then the same thing on the top. And so what we'll do is we'll start our electrons going to our boron, which is our electrophile, and then what we'll do is we'll snap our hydride into the top carbon. So, what do we end up with in that case? Syn or anti? Definitely syn. It's a concerted mechanism. This is all going to happen on one base. And so our methyl, let's push it back. We've added a hydrogen end to the top side. And then on the bottom side, we've got our BH2. Of course, this is also plus enantiomer. All right, plus enantiomer. So this is going to be a stable intermediate. So what do we have to do to get out of a stable intermediate to our final product? We have to use a workup step. Yeah. What's that? Yeah. Yep. Good catch. Doesn't make a lot of sense as written. So this needs to be more electronegative to have that partial negative charge. Yep. Okay. So they're going to be on the same side, and so we've arrived at this stable intermediate. but that's not what we want. We didn't see a lot of drugs with a boron attached to it, right? We probably want to get rid of that. And ultimately, we're going to swap out for that boron. What do we end up with up here? An alcohol, right? So basically, we're going to swap in an OH for a hydrogen. So what we're going to do is a workup step of hydrogen peroxide and sodium hydroxide. So this is going to be an oxidative workup. You're not responsible for the mechanism of these workups, but specifically when we're adding or when we're doing this oxidative workup for the hydroboration, so what we'll see, we're not going to do anything to the top side, but our BH2 is more or less swapped to an OH. And importantly, have we kept the same stereochemistry as the BH2? Yes. Yeah, we do. And so in our workup step, essentially we will replace our BH2 with an OH, and importantly, we are going to retain the stereochemistry. Okay, so, let's see, of course, again, plus an enantiomer. In a lot of these cases, there's always going to be two products possible just because of the symmetry of a pi bond. All right, so let's go ahead and add her into our table and we'll call it a day. So this is reaction number 6. Our electrophile is what? What do we end up with as our electrophile, in our electrophilic position? We swap it, right? It was hydrogen in the earlier cases of our reactions, but now it's the OH group that we've added to our secondary car. And that's what makes this reaction so useful, is now we've essentially swapped our electrophile and our nucleophile. Our nucleophile is what? Hydrogen. Yep, it's our hydrogen is what we end up with on our product. And so, reagents we want to use, you can use BH3, or you'll see B2H6 used sometimes. Same exact mechanism. I'll probably always use BH3 just for the simplicity of drawing. If you're going to buy these things commercially, do you think you can just buy BH3 by itself? Yes. It's open shell, right? And so that's not going to be very... Anything you put it in, it's basically going to form some complex with it. So typically when you buy BH3, you buy it as BH3 complexed with a solvent called THF. And so what that looks like is you have BH. This is what you actually buy if you buy BH3. And it's because when you put the BH3 in the THF, well, we know that the boron's open shell, and we know we've got some electrons on the oxygen, and so just immediately those electrons on the oxygen donate into the boron, and so we have this stable complex. So that's how you buy it. It's BH3 THF. And we have to do, always remember our workup phase, or our workup step, which is hydrogen peroxide, sodium hydroxide. Regioselectivity, what is it? Is it Markovnikov? No. It's not. It's what we call anti-Markovnikov. The only one we're going to see. This is an anti-Markovnikov reaction. What do you think the likelihood on an exam is of me showing you like a starting material and a product and asking you which we need to do, the oxymercuration or the hydroboration?
Pretty high.
It's pretty high. So it's a pretty good exam question. Is it anti or syn? It's syn. And so we'll call it a concerted mechanism. Just like all the other reactions that we'll learn on Wednesday, we'll go through concerted mechanisms. All right, office hour. I'll get the homeworks out this afternoon. I made Friday's homework and then left it at home, and so I'll get it posted. Office hour today, 2:30 to 3:30.
I just have a question. With our fifth reaction, we're anti. Is this one also syn as well?
No. And so let's go back into the. Can you find it in notes?
Professor,
Yeah.
I need to switch a lab. So who did I email?
Did you email me?
No, I haven't.
Send me an email this afternoon.
Okay.
I've got a bunch of things to take care of then, and then I'll get back to you.
Okay.
Which lab are you in?
I'm in Thursday afternoon one,
Okay,
and
so
I
we've
want
got-
to go tomorrow.
That should be fine. Just send me an email and we'll get it worked out.
Okay.
Okay.
And also, where will your office hour be?
I think the room is 2018. I sent it out in that email.
Okay.
What it is you know where the reading room is at the end of the chemistry hallway, like the bookshelf.
Okay. Yeah, I know that.
It's the room above it.
Okay.
So it's just one floor up, right directly above it.
Okay. Thank you.
Yep.
Okay. So it's empty because they're on opposite sides,
Yes, it's anti, and then it's Markovnikov because we end up with our hydroxyl group.
and then we put it.
It's on the tertiary.
Okay. Thank
Yeah.
you.
Professor Walk,
Yeah.
so this is like a question in one of the problem sets.
Okay.
And I'm just wondering, do I need to like draw out like the wedge and dash? Because it doesn't say if it's wedge or dash.
So you want to draw them out if you have stereochemistry, and so in this case, we don't have any
we don't have any,
stereochemistry, and so
okay.
all it can form is one product. So
Right.
you don't have to draw any wedges or dashes
Right.
unless you're showing stereochemistry.
Okay, and also for this anti-insane, so this is anti-insane and plus their enantiomers. Can I say like this is anti-insane? Like, can I place these two together instead of these two? Like,
I mean, it doesn't really matter how you place them as long as in this case you know that there are 4 different products.
oh, so they 4 of them are like all in one product.
Yeah, so they're all
Like a
possible
mixture.
stereoisomers in this case, right?
Okay.
So you've got 4 possible products, and so you've got them down on paper.
Okay.
Yep, and that would be fine.
Okay, thanks. And also, what's the question? Oh, do I attack the compound like with bromide like here or here? Because
And so what you'll find is if you add it to the oxygen, we're still going to have a positively charged oxygen because it's still going to be connected to 3 things. And so you're always going to add it to the carbon.
so like this carbon.
Yep. And so you can draw it to either picture. You can draw it like you've shown it, or you can draw this to the carbon and just show this bond retreating back to the oxygen. You'll end up with the same product in both cases.
Okay, but like this is like a positive hydrogen, oxygen though.
Yeah, it is. And so what are you talking about adding to the positive?
Yeah.
So what happens is we add to the positive oxygen, we're still going to have a charged product, right? Because we're going to have 3 bonds to the oxygen. We'll have that carbon connected to it, that carbon connected to it, and the bromine. And so while you might have some, while they might interact favorably, it's not going to be a stable product because we still have 3 bonds to it. And so ultimately what we want to end up with is a neutral product, and the only way we can get a neutral product is by adding to this position.
Okay.
Yeah,
Thanks.
there's often a lot of routes that we can go, but only one will lead to a stable product.
Okay, thank you.
Yeah.
So I was confused how you got this from like or why did you?
Yeah, and so when we're doing this step right here, we know that our pi bond, as it's shown here, so it's going to be perpendicular, right? So it's going to be perpendicular to our trigonal plane.
Right,
So that means
yeah.
it's above or below. So the electrophile-nucleophile combo can either add from the top side or from the bottom side. And so what I've done is I've flipped it such that now we see our p orbitals are perpendicular in the plane of a paper like this, and so our nucleophile-electrophile can add to the top side of the double bond.
So you're flipping it like this?
Yeah, I'm basically just flipping it such that you can now see the p orbitals straight up and down.
Okay.
Yep.
Okay. And so like these carbons will be like here.
Yep, you got it. And so that's why we end up with both of these things on a wedge or both of these things on a dash, because they've both got to come from the same side, either the top or the bottom together,
Right. Because that's what.
because it's all happening at one point, or at one time.
Okay.
Yep.
Okay. That makes sense.
Okay.
Thanks.
3 questions.
Okay.
Why is this more nucleophilic than this one?
So it's an acid-base thing. So what you find is HBr. Okay, so let's think about their acids. HBr is a strong acid.
Okay.
H3O is also a strong acid, but it's not as strong. And so if this is,
But this is H2O.
yeah, but we're thinking about the basicity,
right.
right? And so what we want to think about is compare the pKs of their acids. So the acid of this is HBr and is a strong acid with a pK around -7. The acid of this is H3O with a pK around -2. And so this has the stronger acid, which makes this the stronger base. And so basicity and nucleophilicity,
Very different.
they're very common. They run hand in hand. And so typically the more basic a compound is, the more nucleophilic it
Okay,
also
so it'll always be the H2O that will stand on to it.